Hello, everyone. I'm Gilad Shiner from NVIDIA, managing the high-performance computing networking technology at NVIDIA. And I'm happy to talk with you today about cloud-native supercomputing, architecture, benefit, what does it mean, and so forth. So when we look on high-performance computing and artificial intelligence, those areas has actually driven supercomputers into wide commercial use as the primary data processing engines enabling research, scientific discoveries, and product management. Now, when one builds a supercomputer, obviously the most important thing is performance. So you're trying to minimize everything that will reduce from the supercomputing performance and give the bare metal performance or even accelerated bare metal performance for the applications running on top of that. So you don't have really elements of multi-tenancy, you don't really have elements of security and isolations and so forth. Main aim is to get the best performance from the system. On the other side, when we build a cloud infrastructure, obviously the main focus is multi-tenancy and performance isolations and user isolations and so forth. And when someone builds a cloud, actually there is a big toll of that data center operating system or the infrastructure workload on the system performance. Now, as supercomputing goes to more and more places, supercomputing will be used by more and more users, by more and more applications. And therefore, actually, we do need to find a way to bring the cloud services into supercomputing without impacting the bare metal performance. On the other side, cloud will actually start to serve more and more HPC users and more HPC and AI applications, and therefore they also need the ability to actually reduce the overhead that multi-tenancy and isolation put on their system or computing resources. And this is exactly what cloud native supercomputing is. Cloud native supercomputing is a combination of bare metal performance on one side with multi-tenancy and isolation and security on the other side. Actually bringing the cloud services into supercomputing and ensuring that we get the best performance, the bare metal performance from the infrastructure that we build. The key element that enables the architecture, the new architecture of cloud native supercomputing is what we call the DPU or data processing unit. And in order to understand what the data processing unit, I wanted to give you kind of a scope of all of the NVIDIA Quantum InfiniBand infrastructure components, not essentially to go into the product description, but just to give you a more or better understanding of what a DPU is. So when we look on the InfiniBand or the components that build the InfiniBand, NVIDIA InfiniBand infrastructure, the high-speed InfiniBand connectivity that is the heart that connects all of the compute engines together to form a supercomputer, we find the following elements. So first we have the adapters, the network adapters or the NICs that we put on every node in every computer. Those adapters can be the ConnectX or a device from the ConnectX family or the DPU. Now the DPU is a silicon device which is a full data center on a chip. The DPU silicon device includes all of the ConnectX inside. So all of the NIC functionality, all of the network services that we put on a server are actually inside of that silicon device. Now the DPU also includes multiple ARM cores, the most energy efficient computing engines, as well as other acceleration engines and a memory. So it's a full data center on a chip that forms or brings us the capabilities of a network adapter, but with computing engines and acceleration engines that help us actually to run the infrastructure management, the infrastructure workload, the data center operating system on the DPU instead of doing that on the CPU. And that's the key element of enabling cloud native supercomputing. Just to complete the infrastructure, the networking infrastructure here, We also need, obviously, the switch, the NVIDIA quantum switch that connects all of the networking devices together. And also important to know that there are other components or other appliances that actually bring foreign capabilities into cloud-native supercomputing. There is the MetroX long-haul appliance that helps to extend native InfiniBand reach over long distances. That enables us to connect the main supercomputer to remote storage or to remote computing engines or resources or systems that sits far away, such in labs, in HPC labs, in instrument that running experiments, to workstations that sits on their researcher desks and so forth. The Skyway appliance, it's appliance that seamlessly connect between InfiniBand and Ethernet. So it enables us to connect the InfiniBand that's running all the communication inside of the supercomputer to the outside world that connects through Ethernet. And last and not least, there is also appliance that runs the UFM Cyber AI capabilities. This appliance enables to bring predictive maintenance as well as more security alert management provisioning of the network and of the data center in a very easy way for the people managing the infrastructure. So those are the components. We're actually gonna touch more about the DPU later on, as well as what are the services that we're actually getting from the network or from the NVIDIA InfiniBand infrastructure. So when we look on InfiniBand, on the NVIDIA InfiniBand technology, obviously InfiniBand is a network and it provides network services. And InfiniBand actually excel in providing the network services, which includes the highest throughput, the highest data speeds in the market, extremely low latency. It's a 2x, 3x lower latency than anything else that exists out there with high message rate. InfiniBand pioneered RDMA, the technology that enables the network to move data directly to the CPU memory, directly to the GPU memory, or from storage to the GPU memory with no involvement of the CPU. So it's reducing the CPU overhead as well as moving data directly to its location. And of course, InfiniBand includes enhanced adaptive routing and congestion controls and quality of service and many other things as part of providing network services. On the other side, one of the big advantage of NVIDIA InfiniBand technology is within network computing. So NVIDIA InfiniBand does not just provide networking services or communication services, it's actually also provide computing services. There are engines inside of the silicon devices, the InfiniBand silicon devices, that include computing engines that can run specific algorithms or can be completely programmable. The engine that runs specific algorithms actually migrate algorithms that traditionally run on an endpoint and move them to the network to run them in much more effective way, to reduce overheads, to improve application performance. We are moving more and more engines or algorithms that are being used in communication frameworks, such as MPI, such as SHMEM-PIGAS, and so forth, to run on the network where they can run in a more effective way and enable us to achieve greater overlapping between compute cycles and communication cycles running the massive parallel applications. Those elements are exposed through a Magnum IO SDK that enables those computing services or make those computing services available for the applications running on top. The pre-configured engines, which includes the ARM cores, the multiple ARM cores inside of the DPU, as well as the programmable data path accelerator, enable us to bring more resources, enable us to migrate the infrastructure workload, multi-tenancy, isolations, file system, storage management from the host into the network, and essentially bring cloud services to supercomputing without reducing the bare metal performance that the supercomputing infrastructure can provide to the users. As well, InfiniBand also includes other engines for security, for storage, and others that works together with the element running on the ARM cores, for example. So when we look on the pre-configured engines, I wanted to give you a couple of examples here. The first example is a technology that is called NVIDIA Sharp. This technology is computing engines, or consists of computing engines that runs on the silicon devices. Those are part of the silicon of the switch silicon device. These engines can get data that comes from the endpoints and run different elements of data aggregations or data reductions throughout the network. And then once having a results for all of the, or for the entire data aggregation protocol, to actually broadcast the result back to the nodes. So instead of doing data reductions on an endpoints, which requires you to move data between endpoints, and the more endpoints you have, it's going to take you more time. It's going to increase the data that needs to move, or to increase the amount of data that needs to move. Running data aggregation protocols on the network reduce data motion and make it much faster. And actually, the network is much more immune to system size, and therefore it gives flat latencies, regardless of the system size, for running data reductions on the network. So the engines, Sharp engines, support different sizes of integer and floating points on all of the data arithmetics. The API is open through Magnum IO SDK, and therefore everyone that creates a communication framework or use reductions for applications actually can leverage the engines on the network to run those algorithms. So what did it give us? As I mentioned before, it gives us flat latencies. So you see an example of running data reductions on the host, on the CPU, versus running data reductions on the network. When you're doing data reductions on the network, you get flat latencies. Network is much more immune to system size. If you build a two-tier switch network and you put another tier, you increase latency in around 200 nanoseconds, but now you connect hundreds of thousands of endpoints together. So that's why you get flat latencies. Obviously, when you're doing the reductions on the network, you also reduce data motion. So those are great benefits. On the right side, you can see the integration of Sharp, of NVIDIA Sharp, NVIDIA InfiniBand Sharp with Nickel, with the NVIDIA Collective Communication Library. And by having Nickel utilize Sharp, we can improve Nickel performance by 2.5x, which obviously will affect the performance of the full applications running on the infrastructure. Another engine, for example, is tag matching. And tag matching is something that happens every time an incoming MPI message is being received. So instead of interrupting the CPU, actually the network device can handle the MPI tag matching. And there are other pre-configured acceleration engines on the InfiniBand network. So what we try to do is try to understand the impact of each engine separately on the application performance. This is a more artificial experiment, because when you're running an application running on MPI, for example, on message passing interface, you have the tag matching part, you have the reduction part, you have the rest of the things working there, and therefore one engine actually fuel the other. But in order just to understand the separate impact of each of those engines, we did an artificial experiments where we disable everything else and look on the effect of these engines on the total application performance, the full data center performance. So when we look on Sharp on doing the data reductions on a network, Sharp includes small message reduction and large message reduction. Large message reduction is more for AI, more for training. Small message reduction is more for kind of classical scientific simulations in a sense. So when we look on the small message reduction, and I show you previous slides, we can see that Sharp increases MPI or reduced performance by 7x. That in turn reduces the total MPI time. The total MPI time from applications in around 25 to 30%, and that increases the total application performance, the total data center performance by 15% and even more. And you see an example of CFD codes and other codes here that can be accelerated just with that specific computing engines that runs on the network. Large message reduction, improve nickel performance by 2.5x, for example. And then we're seeing 15% improved performance for recommenders and 17% performance improvement for NLPs, for natural language processing. So just that engines that improve nickel performance has a good impact on the total data center performance running these AI workloads. The MPI tag matching, again, impact the MPI performance, or improve MPI performance, and we're seeing up to 40%, performance improvement for different kind of applications. In the upcoming new generation of NVIDIA InfiniBand, which will enable us 400 gigabit per second later this year, there are new engines, such as doing all-to-all engines on the network, that will improve all-to-all performance by 4 to 5x. And later this year, we'll be able to see or measure what would be the impact of that specific engine on the full application performance. So now let's go back to cloud native supercomputing. So we see that InfiniBand give us communication services, great communication services, as well as in-network computing services, which are critical to improve application performance. In-network computing essentially transforms the network to be a distributed CPU. It's a new architecture in a sense. New architecture for supercomputing. And now we're taking that into cloud native supercomputing. So as I mentioned before, cloud native supercomputing is essentially the combination of bare metal performance on one side and multi-tenancy and isolation on the other side. Bringing cloud services into supercomputing, bringing supercomputing performance into the cloud. And everything is made available for the first time because of the DPUs, because of the data processing units. So on the right side, you can see the high-level architecture of the silicon device, of the IC, of the ASIC, of the DPU. So DPU, or Bluefield, which is the name of the DPU device within NVIDIA, Bluefield includes all of the ConnectX functionality. All of the NIC functionality is inside of that silicon device, with multiple ARM cores. On the current generation of Bluefield 2, there are 8 ARM cores of A72 64 bits, energy efficient ARM cores that are accompanied by different kind of acceleration engines, security engines, multi-tenancy engines, storage engines, other infrastructure engines. The combination of those hardware engines and the ARM cores and the set of ARM cores enable us to migrate, to offload and accelerate the data center operating system from the x86 or from the host CPUs into the DPU. So instead of having the multi-tenancy support, the security, the isolation, and so forth, brings a big performance toll, a big overhead toll on the host CPUs, we can migrate that workload into the DPU and actually do it or run it much more effective, in a much more effective way because of those acceleration engines. We're not just offloading the infrastructure workload from the host CPU, from x86 into the DPU, into the ARM cores, but we're actually accelerating that because of the hardware engines that works together with the set of the ARM cores. So the DPU has 3 main functions, or serve 3 main functions. One, to enable cloud native supercomputing by migrating, offloading, and accelerating the infrastructure management or the data center operating system. Now, as the DPU is essentially a full data center on a chip, when we put it inside of the server, it becomes a new computer inside of that computer, and therefore it can also help us to further accelerate application performance. So that's the second usage of the DPU. And of course, the DPU being a full data center on a chip is the best component for edge computing. For HPC edge computing, for example, DPU can be used in HPC labs, for example, and be the first device that do the analysis of data being acquired before sending data to the main system. And of course, one can combine multiple DPUs together or form a combinations of DPUs and GPUs and so forth based on the computing needs that are needed at the edge. So when we look on the architecture of cloud native supercomputing, what actually we're doing is we're taking the management, the data center management, the multi-tenancy isolations, the monitoring, the file system management, cluster file system, network file system, all of the infrastructure management, and move that from the host into the DPU. And leveraging software development kits and runtime of DOCA, as well as Magnum IO to provide all of the services, all of the data center services to the applications running on top. So we frame the CPU cycles, we bring bare metal performance, or ensuring bare metal performance, and therefore be able to actually bring the cloud services or the multi-tenancy services for the first time into supercomputing with no impact of performance. So by doing that, we actually moving the supercomputing infrastructure to become more of a zero trust architecture. We bring in the storage virtualization, we're securing the network infrastructure. The jobs, the tenants, the applications running inside of the nodes actually quote unquote locked inside of the node. They don't have a free access outside. Everything is governed by the DPU. Everything is managed by the DPU. And that's why we're moving toward a zero trust architecture. So we have a full isolations between applications. We have performance isolation as well, which is very important. As we have shared resources that are used by multiple jobs, we want to make sure that one job does not impact another job performance. Now, as I mentioned, by having the DPU now in our system, we can use the DPU to further accelerate the workloads that we're running. The DPU is essentially a computer within a computer. And we can use the DPU to form a new hybrid model of a GPU, CPU, and a DPU for running applications within a data center. There are a lot of things we can do with the DPU regarding that. For example, we can offload non-blocking operations, such as MPI non-blocking operations, from the host to the DPU, and with that be able to improve those operations performance, but even more important, to be able to achieve full overlapping. So when you're running a parallel application, we have period of computing, we have period of communications, we have period of computings and period of communications and so forth. And if we're able to hide one under the other, if we're able to hide the communication period under the computation period, we can dramatically improve application performance, and the DPU actually enables us to do that. We can use the DPU for other elements, for user-defined algorithms, for smart MPI progression, and there is a lot of other things or new capabilities that the DPU bring us. So this is an example of running the non-blocking MPI operations on the DPU, and by doing that, we can increase, for example, non-blocking all told by 44%, 36% for all gather, and so forth. And more importantly, as I mentioned, to be able to achieve overlapping. So now we're measuring overlapping between compute and communications, and we're able to get 100% overlapping because of running the non-blocking operations on the DPU, which in turn help us to improve application performance. So this is an example of FFT, of three-dimensional FFT, where we modified FFT to use non-blocking all-to-all operations instead of using the blocking all-to-all operations. And by using non-blocking all-to-all operations, we can use the DPU to accelerate performance, and with that, ability to actually improve FFT by 1.3x. So everything exposed through DOCA, which is the software development kit and runtime. DOCA exposes all the services of the DPU to the applications running on top. The network services, telemetry services, MPI services, management services, storage services, everything exposed to the applications running on top. And by running on top of DOCA, you know that everything written on one generation of the DPU will run the same, essentially faster, on the next generation of the DPU, third generation of the DPU, and so forth. So exciting time. We continue to drive more capabilities for the cloud-native supercomputing architecture. DOCA is the software SDK that enables to expose all the services to the applications running on top to the users running on the cloud-native supercomputers. Excited with Bluefield with the DPUs. We already announced the next generation of Bluefield that will bring us 400 gigabit per second as well, with NVIDIA Quantum NDR InfiniBand technology that bring us the faster speed, bring us in-network computing engines that together with the DPU further accelerate application performance, and of course, great networking services. So continue working on that. Please stay tuned, and you can check the NVIDIA website for more information about cloud-native supercomputing. Thank you very much for listening. There is a live Q&A session starting now to continue the conversation. To take part, join us on Zoom by clicking the yellow button just below the video player on this session's page.